to look at faces, and I would like to see especially the students. Nobody else is going to turn their camera on, okay? I'm waiting. How many of the students, raise your hands like this, I can see. How many of the students have taken physics courses in high school? Some of you, or not all of you, okay? I will try to talk at an average where essentially no science is required, no prior science is required. I see a hand up there. Feel free during the course of this hour to raise your hand and turn your, unmute yourselves and speak. I will give you the floor to ask a question as we go along. And we will also have time at the end if you want to save your questions. I was asked to introduce myself and tell you my story about how I got into science and where I am today. I am an immigrant, first generation immigrant. I have two wonderful daughters that are now second generation immigrants, and they have children, they are grandkids. So that's how it works in America. So I want to tell you some of my story before we talk science. I'm going to share my screen, if I'm allowed. Yes. So what you see on my screen, yes, is a map of Europe and vicinity. And I was born and raised on the island of Cyprus, which is this island here in the Eastern Mediterranean. The coloring here designates the countries in the European Union. Cyprus has been a part of the European Union for about 15 years or so, 16 years maybe. As you can see, it sits in a relatively strategic position at the crossroads of Europe, Asia, and Africa. And it was on the crossroads of marauding armies throughout its history. In the ancient years, this is a map of Cyprus. In the classical Greek times, Cyprus was an integral part of the Greek world. The goddess Aphrodite, or Venus, was alluded to have been born in the waters of the sea by Paphos here. Zeno of Kition, modern day Kitty, was the founder of the Stoic school of antiquity. It's an island with, every country is beautiful, but it has some unique features. I circled here in red. The middle of the island is a mountain, they call it the Troodos Massif, and it's 6,000 feet. Now, the entire width of the island, north to south, is about 40 miles. So think where you live right now, and you can drive for 40 miles and probably not find hardly anything at all. It's either flat or maybe hilly, maybe rolling a bit. But here, 40 miles across, you got to go up 6,000 feet and get back down. So there's mountains up there with snow, and then there is beaches all over the place. I show you one here at the bottom right, and there is scenical beauty on many, many places. This is my hometown in its modern glory. And it actually is beginning to be loaded with high rises now. When I was born, it had about 25,000 people. And I was actually born in a small village outside the town boundaries at the time. Now it's swallowed up, and it's just an integral part of the city that has about, I don't know how many, maybe a couple of 100,000 people. This is the waterfront, which was not like that when I was born. I think that's all the pictures I have about Cyprus. I was born in 1948. I'm 70. I'm going to be 72 next month. 1948, as you remember, it was right after the end of World War II. All of Europe was in shambles. Cyprus had been a British colony in the years when, well, it was part of the Ottoman Empire for 300 years, but the Ottoman Empire was falling apart. And at the end of the 1800s, Britain actually bought Cyprus from the Ottomans, and it became a British colony. And in the Second World War, as I told you, everything was in shambles. But over the years, the British didn't really worry too much about the local economy. So the island was very, very poor. And with the war, everything got worse. So my early years in my little village, it was, we were all very poor. And we didn't get electricity and running water until I was about 5 or 6 years old. So I remember the days before we had, my mother had to go to the local, it wasn't the spring, it was, it led water, they could get water in buckets and bring it home. And we had oil lamps and that sort of thing. A long time ago, when my daughters were in kindergarten, one of them, I was asked by the teachers to go give a talk to kids about how life was when I was growing up. And I remember that very clearly because I told them about no electricity. The kids were sitting on the floor of a gym as I was talking. And this kid right up front raised his hand and he just wanted to ask a question, so I let him ask a question. He said, if you didn't have electricity, where did you plug in the TV? Very good question, eh? So there are important things in life like TV. So I had a privilege of having an older brother and sister. I was the third in the family. My sister was only less than 2 years older than me, about 19 months older than me. And my brother was 5 years older than me. And my parents had only 5 years elementary education. So the household, we didn't have books, we didn't have musical instruments, we didn't have anything like that. But my brother and sister ahead of me were learning how to read, how to write, how to do other things, homework and so on. So I was full of energy and I followed them, I learned from them. My father was a shoemaker and he worked at home. He had a shop right at the street. And the village during the day was essentially dead. Nobody was there. People were at work and there was a grocery store and so on. But the school teachers in the afternoon, there were only 2 at the time, would come around and sit and keep my father company or just chat. And because the coffee houses would open much later in the evening when everybody came back from work. And I would talk with them as a kid and they knew me. So when my time came to go to school as a first grader, I knew enough material and they were sure of it. So I skipped first grade and I went straight to second grade. And that really gave me a lot of energy. I was a very good student. I progressed there. I finished elementary school, 6 years. High school at the time, we had to pay. It wasn't free. It wasn't mandated. It wasn't required. And my father didn't have very much money. So luckily, all 3 of us got scholarships and we were able to go to high school. But just feeding 3 kids wasn't an easy exercise. And it was 1960, Cyprus became an independent state. The Republic of Cyprus was established. It was quite a history to tell you what happened the previous 5 years and how the British agreed to give us independence. And then all that poverty essentially disappeared almost overnight. The island blossomed, tourism expanded, hotels They built dams of the rivers that allowed agriculture to blossom. And within 10 years, I would say it came on par with European countries and it became a developed country very quickly. I left in 1967 after graduating high school. How? I looked for scholarships and I had a number of scholarships to go to Greek universities. And I should tell you that during my high school years, I was aggressive about learning more things than I was learning at the school on my own. And I loved math. Why I loved math? I don't know. I learned how to count in English to 20, by the way, as a young kid. And then we were having English as a foreign language in the elementary schools and on to high school. And by the time I was the American equivalent of freshman or sophomore in high school, I had done so much math on my own that at that point I effectively taught myself calculus. And I started passing exams that were offered by the University of London around the world. And they were essentially entrance exams to be able to enter the University of London. You could accumulate these exams. There were so-called ordinary level tests and advanced ordinary level tests in various topics, physics and math and history. I don't remember all the other things. And in order to enter the University of London, you had to pass 3 at the advanced level and 3 at an plus 3 at an ordinary level. And then you could get in. And I had almost all of them passed, especially the math. Physics, I didn't take the advanced level because you had to do laboratory things. And I didn't have access to laboratories for the things that they wanted us to learn and do. I was fine, but at the time I couldn't find any scholarships in England to apply to, and there was no way I could go. I had cousins who immigrated to London and lived there. They were business people. They had businesses, they were not in the education business. And there was a possibility that I could go there, work for them in their business and study. But I got scholarships in Greece to Greek universities. And then I wasn't sure I wanted to go to Greece. The universities at the time didn't have a great reputation about the way they were run. And I got interested in American universities. And I really didn't know beans about American universities or American life at all. My only exposure to American life was TV, which I didn't watch very much. We didn't have a TV at home. There was one at the cafe that was a youth club as well. And the only thing I remember watching was a series called The Fugitive. You're all too young probably to know about that series.
TV shows matching Fugitive.
That's Siri of my phone talking. So The Fugitive was a story of a person who was he was running away from police because he had done something and he didn't want to get caught. And every episode he would be in some other city and something would happen and somebody would smell him and chase him and that sort of thing. And I remember, in fact, that the few weeks before I left, I watched an episode that was in Chicago outside the Union Station. And lo and behold, a few weeks later, I was in Chicago looking at Union Station. It was an amazing thing. But the only other American movies that we were watching were big class Westerns. So that doesn't give you a picture of what America is really about. With cowboys and Indians, it was. So I told you I was very interested in math. And I learned a lot of math on my own and in school. But I got to the point where I was wondering, what do you do with math? What do you do with geometry? What do you do with trigonometry? What do you do with calculus and differential equations? The things that I learned never really gave me any hint about what to do with them. And I was a little frustrated because I was at an advanced level and I didn't know where math was going. I was interested in physics, but the physics that we were doing in school, I was in a science school. And we did a lot of physics and a lot of chemistry, but they didn't really have math. It wasn't exciting for me. It's one thing to learn about how a flashlight works and things like that in physics classes, but I didn't see the intellectual excitement that physics had. Until in my senior year, we went advanced physics and we got into quantum mechanics. And quantum mechanics is based on differential equations. And for the first time, I saw a differential equation in a book and I understood what they were using it for. And it was just an amazing experience. And I understood something that is very true, that mathematics is actually the language of physics. It's just like you speak another language. Everything is written down in mathematical form. And nature behaves according to those laws. And you have to solve those equations, the differential equations of calculus. And I got very excited and I said, I want to study physics. What do you do with physics? I had no idea what a physicist does other than becoming a teacher. And I said, all right. I applied for scholarships to America. I had fellowship scholarships for Greece, and I got a scholarship in America. It was a Fulbright scholarship, and it had problems. The fare was paid. I came to America. They already also set me up to spend my first month with an American family, and I spent it in LaGrange Park, Illinois, outside Chicago, with a couple in their 30s. And they introduced me to other Americans and the families who had children my age. It was a very nice month. And we drove down to Indiana where her parents lived. They were very well-to-do and they lived in a beautiful house overlooking the river. So I saw American life in many of its ways. That was a very good month. And then I started my schooling at Northern Illinois University. And I had a scholarship that paid for everything. But when I gave the appointment letter, there was a funny clause there that I discussed with the local people at the American, it wasn't the embassy, it was, I think it was called the Institute of International Education. No, they offered the scholarship along with the Fulbright program. I don't remember what the office, the US office in the capital, Nicosia, was called at the time. But the director of that office looked at the letter and he said, don't worry. The funny clause was that the scholarship was for 1 year and it was not renewable. And he said, don't worry, that's what they say, but they automatically renew them if you are doing well. I didn't like it, but I figured, all right, that's what they say. I'll go along. That's my one choice that I want to go to America. Well, lo and behold, I started. And within months, I talked to the foreign student advisor and found out, no, my scholarship was not renewable. So what are you supposed to do? What do you mean it's not renewable? Well, they didn't know. So I had a big problem. I learned that within a couple of months, by October, I think, when I started. And I said, well, I have to solve this problem, and nobody could help. We didn't have any money. I wrote back to Cyprus and complained, and they didn't know what to do either. So I said, I got to finish, and I got to finish fast. I can't finish in a year, but I'm going to do something about it. I learned that the university had the option, if you felt like you were proficient in any particular course, you could be given a proficiency exam, and if you passed it, then you got the grade and you got the credit units. So I did that. I had a lot of math under my belt, and I took math courses. I went to the bookstore and found out and would look at the books about the courses that I thought I might do well. And I would read the books and I would go take exams, and I passed a lot of proficiency courses. But I needed money for the second year. So I applied for a position as a resident advisor in a dormitory, which would cover the big cost of dormitories. The fees were not very big, and I got some minor scholarships. They were not that big, but I got scholarships for a few $100s. I applied, and I remember back later at the end of the year, it was April, when I found out that I didn't get it. And I was desperate at the time. By the end of the first year, I actually accumulated enough credits to be a junior. I got 2 years worth in 1 year. And when I found out that I didn't get the job, I was at the edge of a cliff. I had no idea how I was going to solve my problem. Luckily, a week later, one of those that got the offers to be resident as advisors didn't take the job, and I was next in line, and my problem was solved. I became a resident advisor, and it was my second year in the United States, and I didn't really know enough of the culture. It was a difficult job, but I did all right. And by the end of that second, I went to summer school, both summer school, regular summer school, and short summer. I think there was a 3-week session after the regular summer school. And in the 2 years and 2 summers, I finished my bachelor's. I was determined to do that because I didn't know how I was going to survive economically. From there on, at the end of my first year, I sat for the graduate entrance exams. They are like the analog of the ACT, or it's called the GRE. And I took it in October of my first year, essentially. Of my second year, October of my second year. And I did very well. I got offers from several schools around the country. And the best offer was from the University of Illinois at Urbana-Champaign. And they gave me a fellowship, which meant that I didn't have to be a teaching assistant in the first year as normally people are. So it worked out. I went there. And I guess I didn't tell you, when I was applying for the scholarship, I was still enamored with math and uncertain about physics. And I remember when I was filling out the form and I said, well, what am I going to major in? And I remember when I said, I'm going to do physics. And I wrote that down, like I told you. I didn't know what physicists do other than teaching. It was at my undergraduate school where my physics professors invited me to participate in research they were doing. And I understood that physicists do research and they can get jobs in industry as well, and so on. So I was hopeful that I made the right decision and I would become a physicist and get a job. And so I did. I got my PhD in Champaign-Urbana 3.5 years later. Then I got a postdoctoral position, which is called postdoctoral. It's an appointment that you have, and you are supervised by a professor to do research in using funds from his grants that has a research program. So from Champaign-Urbana, in which my last year as a graduate student, I got married to an American girl named Mimi, and I am still married to her. We are about to celebrate our 50th anniversary next year. We got married in 72, so it will be in 72. We will, in 2022, we will be married for 50 years. And we spent 2 years in California at Stanford, an amazing place to spend a couple of years near San Francisco. And after that, I got a job at the IBM Research Center in New York. At the time, it was one of the family jewels of American research, along with the Bell Laboratories. Bell Laboratories was funded through a tax on telephones. The telephones were regulated. Only Bell Telephone was allowed to provide service by telephone at homes and everywhere. And there was a 2% tax on that for the research laboratory of Bell Telephone. And they had an amazing research laboratory. IBM on its own developed its own research laboratory. They were also, they were in effect a monopoly like the Bell Telephone, but not a legal monopoly. It was the only company that was making big computers, mainframes. And everything was run at the time by mainframes, but computers were not very powerful. They had the power of what calculators can do today. So just a second. So that's pretty much my story. After I spent I spent 20 years in New York at the IBM Research Laboratory. During my thesis work at the University of Illinois and then at IBM, I was doing research in materials called semiconductors. Semiconductors are the basis of all electronics, computers, the chips that run computers, the lasers, solid-state lasers are made from semiconductors. Light-emitting diodes are made of semiconductors. Basically, all kinds of electronics are made with semiconductors. Those were the big research areas in the 1970s and 1980s. And then it expanded in all kinds of other materials. I left IBM in 1994 and joined Vanderbilt University. And I've been at Vanderbilt in the last 26 years. And like other professors, I raise a lot of research money from federal agencies. And I have what are called postdocs and graduate students. And we do primarily research. We teach, most of my teaching is teaching graduate students. And I was, for a number of years, I was teaching, I developed my own course called Physics for Everyone. And it was for all grades. Everybody could take it as an undergraduate and it would fulfill their science requirement. And it didn't have any math or prerequisite. And I enjoyed doing that for a while. Now, the last couple of years, I started teaching a course in nanoscience and nanotechnology, which is a new frontier in the last 20 years. And what I'm going to tell you, I'm going to stop here. And if you have any questions about all the things that I told you about my professional life, you can ask them now. Otherwise, we will start. I will tell you about nanoscience and nanotechnology. Any questions now? Okay. So the wide world of materials, one atom at a time. Materials are made of atoms, right? Atoms is a concept that was created for the first time by Democritus in ancient Greece, who had a very simple idea. And he got it by realizing that if he was sitting in another room in his house and his wife was in the kitchen cooking, he could smell the food, but he couldn't see anything. And he realized that some very small things that I can't see are coming from the kitchen and go in my nose. And then he had the idea that if you take anything, you can keep cutting it and making it smaller and smaller and smaller. And he asked the question, how small? Do you have to stop at some point? And he had the genius idea. He said, yes, you have to stop at some point. There is something at the bottom of it all that is called atomo. Atomo is a Greek word that means the uncuttable. That first letter A is we use it in English to negate, just like in Greece. Like we can say amoral means without morality. There are other words like that. So temno is the Greek word for cut. So atomo means the uncuttable. Well, today we know what atoms are, but it took a long time to figure out what atoms exactly are and the periodic table of the elements and all of that. Today, we know, we learned over the years through experiments and theory that the atom is made of a nucleus at the center, and there is electrons around it, and the nucleus carries a positive charge. The electrons around it carry a negative charge, so the atom is neutral. You have seen this image of an atom, of a nucleus at the middle, and electrons buzzing around in orbits like the planets do around the sun. This is wrong. It was a model that was invented in 1913 by Niels Bohr to account for observations at the time and the breakout of the failure of classical physics to explain a number of things. And the only way to explain them was to propose that atoms are like this. He got the Nobel Prize for it, and he deserved it. Sadly, they still teach this in schools today. We know better now. They are not like planets. The best way to think of an atom is a nucleus, and electrons around it is like a fuzzball. It's not, an electron is not really like a billiard ball. It's a distributed object, and we cannot describe it the way we describe mathematically a classical particle. You all know Newton's law, F equal ma. An object has a mass, it's there, it has a velocity, it has an acceleration. We know exactly where it is at any time. And F equal ma, by the way, it's a differential equation, but they don't tell you that in high school. And you can solve it and find out where you can get the trajectory of any particle. That's how they do when they landed on the moon. They kept solving those equations to find out the trajectory and exactly how it's going to land and where it's going to go. Electrons don't behave like that. Electrons are described by a completely different kind of differential equation, and it tells you a distribution, not a position. So we only know roughly where electrons are distributed. They are around the nucleus. It's a fuzzball. You can draw it like this and show the water molecule where you have an oxygen nucleus there, and you have a proton, a hydrogen nucleus here. The electrons are the fuzzballs around them. These little dark circles, that dark blue things, the artist drew them like that to suggest that there are 6 electrons in a shell here. There are 2 electrons that are inside the shell, in the inner shell, and so on. And the hydrogen is this, it's like a shell. You can think about shells. This fuzzball has a kind of a shell structure. That's all right. So this is what molecules are. And we often depict molecules by drawing little spheres, little balls, connecting them with sticks. This is a chemical bond here between an oxygen and a hydrogen. We call them chemical bonds. It's overlapping distributions of electrons that make the bonding. It's like holding hands, all right? And we draw them like this. This molecule is an aspirin, and these are carbon atoms. The red ones are oxygen atoms. The white ones are hydrogen atoms. Now we're going to get to the nanoscale. How small are atoms, and what is the nanoscale when we talk about nanoscience and nanotechnology? You know what a meter is? You can go up to 1,000 meters. You can go to 1,000th of a meter or a millimeter. 1,000th of the millimeter is a micrometer or micron, and 1,000th of a micron, which is the nanometer, and that's effectively a billionth of a meter or a millionth of a milliliter. So a billionth of a meter. And we can write the powers, I'm sure you're familiar, 10 to the third is 1,000 meters. 10 to the minus 3 is a millimeter. 10 to the minus 6 is a micrometer. 10 to the minus 9 meters is a nanometer. It's hard to conceptualize, however. What's 10 to the minus 9 meters? Atomic radii, the atoms have different sizes depending on the number of electrons they have. They grow. And down the periodic table, this is the second column of the periodic table, and they range at all fractions of a nanometer. The hydrogen is the smallest, cesium is the largest, and it's a quarter of a nanometer. So the diameter of atoms range from 0.2 to 0.5 nanometers. So we have about 2 to 5 atoms in a nanometer. So how big is the atom and how big is the nanometer? Okay, a nanometer is a billionth of a meter. How do we conceptualize that? And of course, if you take atoms and make molecules, you can get a few nanometers. So molecules are in the nanoscale, if you will. There's a big one, a big wheel molecule that can be quite substantial. Let's look at how many atoms are in a human hair. Across a human hair, if we take the thickness of a human hair and blow it up, it's actually 100 microns, which is a 1/10,000th of a meter. A hair is 100,000 nanometers. Huge by the scale of the nanoscale. So there are 200 to 500,000 atoms across a human hair. The nanoscale now is defined as objects with at least one dimension, X, Y, or Z. We have a three-dimensional world. At least one of those dimensions is smaller than 100 nanometers. That's the nanoscale. So in that dimension, or more than one dimension, that is only 100 nanometers or less, we have 1 to 500 atoms across. And if they are smaller than 10 nanometers, they only have 20 to 50 atoms across. So we are playing with atoms in the regime of nanomaterials. The thing that makes nanoscience so important is that nano objects have markedly different properties than the bulk material. Markedly different properties that we can take advantage of. The bulk materials, the ones that we use for high-tech devices and electronics and so on, as opposed to materials that we make bridges with or aeroplanes, are crystals. In a crystal, all the atoms are arranged periodically in a form like this. This is one possibility. And you can draw them like this schematically, or like this. You can see the pattern, it's like the floor with tiles. There's stacks of them in a three-dimensional material, three-dimensional world. Here's an example of a material that has a very complicated periodic structure, and there are 4 different chemical elements in here. There is copper and oxygen, carbon. I think it's barium, the other material. It's YbCO. Okay. Other materials are not perfect crystals, are polycrystals. That means they have pieces of crystals. You see this piece is oriented this way, this piece is oriented this way, and they join in the middle here. So it would have regions of crystalline material that join in all different ways. And most of the materials that we use for structural applications, like making bridges and aeroplanes, are polycrystals. Now, a bulk material typically has 10 to the 22, 10 to the 23 atoms per cubic centimeter. All right. So the nanoscale is just a tiny piece. There are other materials that don't have a crystalline behavior, and they're called amorphous. There are polymers that look like this. chains of carbon atoms and so on. And a protein looks like this. There are also now today, with the advent of nanoscience, what we call nanostructured materials. So the material may have structure like this on the nanoscale. You can see here, the 100 nanometers is right here. So we have nanostructured bulk materials. But nanoscience, quite the bulk, the essence of nanoscience is really nano objects. Nanoparticles is one of them. Nanoparticles are little guys that have essentially nano, they are nano in all three dimensions, X, Y, and Z. So they are up to 100 nanometers. We call them nanoparticles. And gold nanoparticles, when they are 180 and 70 and 60 nanometers in diameter, they are gold looking. This is in solution in some organic solution. They give a gold color when light strikes them. They reflect light that looks gold. When you get down to 20 nanometers, the gold nanoparticles start looking red. It's a smaller number of atoms. Now you can count them. You are talking about 100 atoms, or 150 atoms. They are not arranged the same way as in the bulk material. These big nanoparticles, the atoms are arranged as in the bulk material mostly. Then once you get very small, the atoms are arranged differently. They have completely different properties. And one of them is their optical properties. What do they look like when light shines on them? Here's another example that was done by Sandy Rosenthal here at Vanderbilt a few years ago. Cadmium selenide nanoparticles, they're again in solution. And if you shine UV light on them, they look red, they emit light back. Red, you get them smaller, they're yellow. Smaller, they are green. Smaller, they are light blue. Smaller, they are blue. It's the rainbow of colors. As you get smaller, the color changes. I'm going to tell you later what controls this color. They were having difficulty making them smaller than 2 nanometers. 2 nanometers, they have a few dozen atoms. They had difficulty making them smaller than 2 nanometers. And then one day they succeeded. They expected that the color they get, if they make them slightly smaller, the color would be purple. That's the end of the rainbow. Dark blue to purple. They were very surprised they got white light. Totally unexpected. And for 5 years, nobody could explain it. We explained it. I'm going to give you an example of my own science later on. So this is again an example of how nanoparticles change their properties. This is, I'm talking about optical properties, but their magnetic properties change, their thermal properties change. Every conceivable property is different than in the bulk material. Nanoparticles have a lot of uses. And one of them that is really getting bigger and bigger by the day is nanomedicine. Here's gold nanoparticles. You can put them inside the body and they go in the bloodstream. By attaching different molecules to them like this, you can select the molecules that make them very likely or most likely or almost certain to go and they stop when they find a cancerous tumor and attach themselves. Because of the different chemistry of the tumor, you can select the molecules that they will go and bind to the cancerous tumor. And then you can do all kinds of things. In some cases, you may fill the nanoparticles with medicine. And instead of doing chemotherapy, or you take it in by mouth or by intravenously, and it goes all over the place, and you try to kill the tumors, and you at the same time do all kinds of other damage. As you know, chemotherapy is really awful. You can put the medication in there, take it to the cancer cells, and release it in there. Other uses of nanoparticles, you get them into the cancer cell and you use radiation. Radiation normally, again, does a lot of collateral damage, but if you put nanoparticles in there that you chose for a particular purpose with good science, they would absorb the radiation. So you target it there, the nanoparticles absorb it and re-emit it right in the cancer, in the tumor. A lot of these applications are under trials now, and some of them have already been approved. It's the future of medicine. I'm going to give you a little bit of history. I'm not going to be able to finish my, Diana told me I can go a little bit past the hour. We'll see what we're going to do. Nanoscience and technology, nanotechnology. Richard Feynman, one of the most illustrious physicists of the 20th century, in 1959, I was only 11 years old at the time, wrote an article called "There is Plenty of Room at the Bottom," and remained historical. He asked, can we put the entire Encyclopedia Britannica on the head of a pin? And his answer, yes, we can. He figured out how big the atoms must be, how many atoms are crossed, and he says, not a problem, we can put it, we just have to figure out how to make the letters so small. He said, at the time, computers were huge. I will show you what computer. 1959, there was virtually no computer to speak of, but there were some, but they were mammoth, all right? He said, we can make denser computer circuitry to make small computers. Well, you know about small computers now. Your phone is a computer. He talked about tiny tools, real tiny. And he talked about microscopes that would be 100 times more powerful than we have in 1959, able to see atoms with a microscope. He envisioned that. And he said, why not? Why can't we manipulate atoms to create tiny structures? And he said about swallowing the doctor. That's something is done today already. That doctors go in with a wire and put a camera in there and watch what's going on in there. So why can't we do that? All right. Those visions have become reality. Nanoscience was instigated after that. People were not talking much about it. But in the 1980s and 1990s, there were a few discoveries that ushered us into nanoscience, nanotechnology. The very first nanoparticles were made. They used lasers and blasted silicon, and these things were flying apart. They were collecting them and studying them, and they could make them 50 nanometers and very much smaller. This is an example of 50 nanometers. The fullerenes were discovered in I didn't put the year here, 1980s, I think, late 80s. They got the Nobel Prize in 1996. This is carbon atoms in the shape of a soccer ball. They're called fullerenes, it's 60 carbon atoms. And carbon nanotubes, which is a sheet of graphite that today we call graphene, made a tube like that. And this is 1 or 2 nanometers, 3 nanometers, that sort of thing, the diameter. So these things happen in the 1990s, 80s and 90s, random events around in the science world, and the scanning tunneling microscope that could see atoms. It wasn't the first to see atoms, but this was a major discovery for nanoscience. And you can see this is a sheet of graphene, a flat thing of this, and these are carbon atoms. We'll come back to that. Kurt Binning and Heini Rohrer did that in 1986. They got the Nobel Prize in 1986. They announced their discovery just a few years before that. So these things ushered the world of nanoscience, and many funding agencies got together about agencies in Washington, federal agencies that fund research, like the National Science Foundation, the National Institute of Health, American the Department of Energy, the Department of Defense, and professional societies, the American Physics Society, Chemical Society, the Institute of Electrical and Electronic Engineers, and so on. They all got together and convinced Bill Clinton, our president at the time, that nanoscience is emerging, and it's the best thing since sliced bread. All right. And they got him to support it and started this initiative in 2000 and started putting in billions of dollars. And all of us got research money for that and worked on nanoscience and nanotechnology. So nanoscale structures are made from atoms that normally make up solids, but they're arranged differently. We saw nanoparticles. Sometimes they're called, some of them are called quantum dots. And there are 3 nanoscale dimensions and 0 macroscopic dimensions. We call them 0-dimensional because they have 0 macroscopic dimensions. This is nanotubes, and there are nanowires, nanoribbons. So 2 of the dimensions, X and Y, are nano, and the third one can be very long and macroscopic. So they have 1 long dimension. Then there are 2-dimensional materials like graphene. It's a sheet of graphite. Atoms arranged hexagonally and flat as opposed to cylindrical. And therefore 2 of the dimensions are macroscopic, and 1 of them, up and down the plane, is just 1 atom thick. Other 2-dimensional materials may be a few atoms thick, but there's a plane and there are a few atoms thick going around. We have discovered by now hundreds of 2-dimensional materials that have unique and unusual properties. And using nanostructures, you can make nano devices. All of our electronics and LEDs and solar cells nowadays are nanostructure, are nano devices. We saw the nanostructured materials, and then nanoprocesses. Nanocatalysis, if you happen to know what catalysis is, it enhances chemical reactions. Nanofluidics, nanomedicine, it's a big deal. This is the world of nanoscience and nanotechnology. So Feynman's vision 60 years hence. Do we have microscopes that are powerful enough to see atoms? Yes. Can we manipulate individual atoms and form nanostructures? Yes. Optical microscopes that you are used to, you put your eye on there, you put a slide there with things on it, and you see them bigger. Normal light strikes the object, and you may have, some of you may know in physics classes how it's enlarged. So you have an object here, the light comes on there, but the lens bends the rays and the eye thinks that the ray comes from here. So you see this virtual image that is much larger than the object. There are more complex optical microscopes, but light cannot help you see atoms. The reason for that is that light is a wave, just like sound is a wave and has a wavelength and a frequency. The wavelength is the distance between crests and valleys of something that is waving. And light waves have a wavelength. And if the wavelength is large by comparison with what you want to see, you are not going to be able to discern it, to resolve it. If you have 2 objects like that, you need a wavelength that is smaller than the distance between the objects for the microscope to be able to see and resolve the 2 objects. Wavelength of visible light is 400 to 800 nanometers. Atoms are smaller than a nanometer. Visible light is hopeless to see atoms. Distances between atoms are a fraction of a nanometer. But electron beams are also waves. They behave like waves, but they have a wavelength that is smaller than a nanometer. Bingo. Use electron beams instead of light to make a microscope. Scientists figured that out. This gentleman did it in 1931, and they made a microscope that is very large by comparison with optical microscopes, about the height of a room. And it's very similar in nature, but instead of glass lenses, they use electromagnetic lenses, electric and magnetic fields. And they have images of materials on the atomic scale. But seeing individual atoms wasn't possible in 1931. They got a Nobel Prize 55 years later. Microscopy, electron microscopy evolved very slowly. In 1970, this fellow, Albert Crew, had the idea of a scanning transmission electron microscope. So this is a transmission microscope. It's not a reflection microscope. The electron beam goes through the sample. So you need a very thin sample. And the way you image it is that in both cases here, you scan the beam, you go through, this is columns of atoms, and the beam gets scattered by the nuclei. When you are between the atoms, they don't scatter, but when you are very near the atoms, so you need to focus the beam on the nanoscale. And they get scattered and get collected into this ring detector, and you form an image. The intensity of scattering is what you plot, and you look and see where the nuclei are. Feynman's dream. He was talking in 1959. Here's 1959. And the transmission electron microscope, he said we have to go 100 times better. At the time, he was talking about this. He wasn't aware that they were already at the 1 nanometer. He thought they were at the 10 nanometers. And he knew he had to go 100 times to 1/10 of a nanometer to see atoms. 1960, that's where he was. Feynman's dream has been fulfilled. Microscopes evolved. By the year 2000, we were already at resolution of 0.1. And then aberration corrections, I won't tell you what aberrations are that were limiting the microscopes. The theory of aberration correction was there, but its instrumentation was a nightmare. It was done. And now we have resolution that is a fraction down here. And we see atoms like you've never seen them before. Here is gallium arsenide and bulk material, the columns of atoms very close together at this perspective. And you can differentiate between gallium and arsenide. They are almost next to each other in the periodic table, atomic number 31 and 33. The intensity is roughly proportional to that atomic number square. You can see gallium and arsenic in there. Here is a stunning image of graphene, a two-dimensional material. This is a schematic, and this is a picture of it. These are carbon atoms, individual carbon atoms. And this is a photograph of them. The color is an artist's rendition. The photographs that are taken are grayscale because it's just an intensity variation, okay? You only have an intensity variation and you color it to give you this impression. Here is another piece of graphene, and you can see there's something going on in here. My friend, would you? This is all I'm going to show you, things that I participated in the research. My own work is theoretical. I solve equations and describe properties and structures. I don't take pictures. But you can see instead of 6-member rings, we have 7 and 5-member rings going on, and here there is a defect. This is a boundary between graphene that points this way and graphene that points in a different direction. Right? Here's a hole in graphene with silicon atoms passivating the edges, and it remains very stable. This is an atom with a high value of Z, and you can see how bright it is. It turns out it's silicon. This, by the way, I'm sorry, these are also silicon atoms. So you can see the pictures that we are getting and the dimensions, 0.3 nanometers across here. So we see atoms, all right. Now watch this. 6 silicon atoms in graphene, and they are not static. One of the silicon atoms jumps back and forth, and you saw some streaking there. Watch. Bang. It's like half atom over here and half atom over there. How can that be? There. It's because you form me this image by scanning. You go like this, And when you are over there, the atom is over here. When you come back, the atom has moved. That gives you the rate at which the atoms are jumping. And we calculated a lot of interesting physics with this. A student of mine, Junhao Lin, was using an electron beam in the microscope and drilled holes in a two-dimensional material called molybdenum diselenide. It's 3 atoms across, not a monolayer, not just a single atom. You can drill a hole and drill a second hole next to it and thin it down to a fat wire. And then by the same beam that is imaging it is doing the sculpting. And if you look at that nano fat wire, you can sculpt it and watch what it does. I'm afraid I'm not going to leave much time for questions, but I want to do this. I'm going to jump quickly now. So let me show you this. This is MoSe2 selenium. Watch this. Under the electron beam. It peeled off and we are down to 3 atoms, and look at how robust it is. It doesn't break. 3 atoms across. And this is a metallic nanowire. You can use it to make interconnections between devices. I was going to explain this to you, how it works and why white light. We don't have time to do that. I'm not going to do it. But it is because these things are at the large 5 nanometers, 3 nanometers, you have crystalline structure. When you go below 2 nanometers, and there's something wrong here, and I'm going to show it to you like this. It's fluxional. They made a movie out of it. It's not crystalline, and that's what makes it give white light. Okay. And we did a modeling of it, and here is the model. It's not going to work. Okay, I'm almost done. I wanted to tell you about electronics. This is the first computer in 1945. It had 20,000 vacuum tubes. This is like light bulbs that they had to use in there. Now we use solid state transistors. The chip in your laptop has about 10 billion equivalents of vacuum tubes. 10 billion devices. This first computer had only 20,000 vacuum tubes, and they were burning out and they had to replace them. 1,800 square feet, 30 tons, and couldn't even do the things that your calculator does. Then the first computer, modern computer, was the Univac in 1952. IBM had its first computer in 1953. These were 9-ton machines. And you could rent them for $15,000 a month. The devices that are going in there to make your chip started out in the 1970s, 10 microns across. This was a slide made in 2015, when they were about 10 nanometers, 11 nanometers. And the projection was that it was going to be 7 nanometers in the year 2020, and we are heading for 5 nanometers. The laptops that you buy today have chips with devices that are only 7 nanometer features. So the nanoscale rules supreme in electronics today. And other big applications are nano energy and nanomedicine. I'm going to stop there. And we have a few minutes for questions. Sorry, I prepared more than I thought I would cover. So, do we have questions? You know, I teach a course on this for a whole semester, so I try to give you a tidbits in a half hour.
We have a question in the chat. I don't know if you can see that with the screen share. Oh, what is the significance of the hexagonal structures in a lot of nanotechnology?
The hexagonal structure is a preferred structure in two-dimensional materials like graphene. this hexagonal structure, nature prefers it when we have a two-dimensional material. Most of them are like that, but not all of them. There are some square structures, and the way atoms are arranged controls their electronic properties, which then control all the optical, magnetic, thermal, you name it, all the properties of the materials for devices other than structural materials are controlled by that. So that's nature.
Thank you.
Yeah. Another question?
I have a more broad question.
Yes.
What do you think for, like as a professor, what do you think is the biggest advice that you give to students, whether they're in college or high school?
Advice? In high school and you're facing a choice of career, right? Well, I'll tell you, high schools don't really provide you with sufficient information about the potential careers. Engineering is not taught in high schools. So I always wondered, how do students decide to go and go into a major in engineering, whether it's electrical engineering or chemical engineering? Usually those are influences that come from parents or uncles or role models of people that you know, and so on. How do you know that you're going to like engineering? How do you know that you're going to like to become a doctor? How do you know that you're going to like to become a lawyer? So you take courses in high school, you learn history, you learn biology, you learn a lot of different things. So, an advice would be, try to figure out what is it that you like, that turns you on. Do you have a passion for something that you like in high school? Follow your nose. I had the passion for math and I didn't go wrong. I don't know if I would have liked it if I had become a mathematician. I have mathematician friends and I have very high respect for them. I am much happier than I became a physicist than a mathematician. Mathematicians would tell you they are very happy to be mathematicians. But you have to have a passion for something. I probably would have been happy being a mathematician. I would have enjoyed it. If you can identify something that you really like, now you also have to measure that, however, against potential employment. I told you that I didn't have a clue about what physicists do when I decided to do physics. But in those days, it was virtually impossible to get information about anything. You had to go to a library and look in encyclopedias or look at. There are university catalogs that had course descriptions. They didn't really have much else. So information, you had to ask your teachers to get some information about it. Now there's a lot of information around there. And, but the first degree, bachelor's degree, it's probably not terribly important what you major in. Get a good education at the bachelor's level. If you can do it in an area that you like, so much the better. If you ask also, I like that area, what are the potential employment pathways there? That's a good question to ask. And you can ask your professors, your teachers to tell you about what are the employment pathways if I major in that or another. Because you can get carried away sometimes and major in something that then you find out after you get your bachelor's, what do I do with it? And there may not be opportunities. It's not a total disaster, because if you have a good education, that will count a lot. But then you would have to be willing to take a job somewhere that is not quite what you studied and be willing to learn new things. And if you go on for a PhD, that degree effectively teaches you how to teach yourself, because you have to come up with original research and defend it. And there's a level when you stop taking classes in your last 2 or 3 years, you are learning by yourself, and with the advice of your thesis advisor, you are creating new knowledge, and you are at a stage where you can teach yourself anything you want. That's the power of the PhD. And if then you have the ability to say, I can get employed anywhere. And people with physics degrees have been employed by the financial industry, by the medical industry, medical world, all over the place. Physics is a good degree to have because it teaches you how to solve problems better than any other discipline, probably. But you have to like math. If you don't like math, that's not the thing for you. There is humanities and other areas. Anything else I can chat about?
Someone asked in the chat, let me see. Have non-repeating patterns / structures been synthesized like Penrose shapes?
I couldn't quite understand you. Say it again.
Yeah. Have non-repeating patterns / structures been synthesized like Penrose shapes?
Yes. Yes. Then there is something called quasi-crystals that are not fully repeating periodic structures. Penrose tiling is something that illustrates that. And the fellow that discovered them got the Nobel Prize. But they're not very widespread things. They just exist against all laws of nature.
All right, it's 4:14, so if you guys have any questions, this is your time.
Last question. Who has it?
Do they exist, like, do the Penrose shapes exist on 2D planes, or is it mostly 3D? Because I remember quasi-structures are 3D versions. So, like, you know how I got this question, like, idea because, like, Justin was asking about, like, the periodic shape of, you know, the hexagonal structure. But has there ever been, like, a flat sheet, but it's non-repeating structure or non-repeating shape, essentially?
I'm not aware of anybody reporting a two-dimensional quasi-crystal. I don't follow that world, but I don't believe, I think 2D would be more easier than 3D to make the non-periodic structure. Whether anybody has done it or it happens naturally, I am not aware of, I'm sorry.
Okay.
But you can easily Google it. If you go to Google Scholar and say, two-dimensional quasi-crystals, they're going to pop.
Yeah, thank you.
You're welcome.
All right, awesome. We are perfectly on time. So if you guys have,
Excellent.
I think there's no last thoughts. Thank you so much again, Dr. Pantelides, for telling us about your career pathway, about